For today's lesson, we will be discussing about the critical points and extremum of a function. So let's discuss first what is extrema of a function. So the extrema of a function are the minimum and maximum points of a function. So when we say minimum and maximum, these are the highest and the lowest points in our function in a given interval. So the extrema of a function can be either relative or absolute depending on the interval and the function itself. So again, when we say extrema, we are talking about the minimum and the maximum points, or the highest and the lowest points in our function. So let f be a continuous function on an interval ab containing x of 0. So this point, if we substitute it into our function and it is less than f of x for all the values of x in the given interval a and b, or a to b, then we will refer to it as the minimum value of our function. Okay? And if we substitute this particular value, x of 0, into our function, and it's greater than all the values of x for our interval ab, then we will refer to it as our maximum value. This is just an illustration of the relative and absolute extrema of our function. So for every part of our curve, there is this highest point, then we have the lowest point at certain parts of our function. Okay, so this one here, the highest point in our function from this particular interval is what we call as the absolute maximum, because that is the highest of all of the points in our function. We are looking at the y values of our function in order to determine the highest one. So here, this one is at 1 only, this one is at 1 also, this is 0, this is -2, then we have here 3. So that is the highest point. So that is our absolute maximum. Now the lowest point among all of the points here, all of the turning points that you can see here, this one is what we call as the absolute minimum. So what's the difference between the absolute extrema and relative extrema? So when we're talking about absolute extrema, we are referring to the highest or the lowest point of a function or curve on a specified interval. So let's say in this given interval, this highest point right here and the lowest point is what we refer as our absolute maximum and absolute minimum. Now you will notice there are a lot of curves or turning points wherein it becomes the highest point at that given interval or that given specific part, or it becomes the lowest point at that given specific part. For example, this one. This point right here is the highest point on this interval or at this part. This point right here is the lowest at this part, right? This one. This one is the highest point at this particular interval. So if that's the case, we are now referring to the relative extrema. So these are location on a curve where all points near it are lower or higher. So for example, this point right here, this is an example of a relative maximum. Why? Because the other points besides it, before and after that particular point, is lower than our relative maximum. This one can also be referred as our relative minimum because it is the lowest point in this interval, and all of the points after this given point right here are higher than this one. So this is an example of a relative minimum. And then this one is also a relative minimum because at this particular location, this is the lowest point, and all of the points before and after that one is higher compared to this point right here. And this one is what we call as a relative maximum because this one is the highest point within this region, and all of the points after the relative maximum and before our relative maximum is lower than this particular point. So we can also think as the relative maximum as the turning points in our curve or in our function. And one thing that we have to remember is that there is only one absolute maximum and one absolute minimum in our function, because we are just referring to the highest and the lowest. So there's only one absolute maximum and one absolute minimum. But for relative absolute and relative maximum, there can be a lot of them in our function or in our curve. So each turning point in our function, they can be considered as our relative minimum or relative maximum. Okay? So this is just an illustration so that we can see which one is our maximum and minimum point. So here we have this curve at this given interval. So this point, negative 1.509, 0.9. So this point is the highest from our graph on this given interval, and then this point right here, this is the lowest point in our graph. So since this is the highest, this is the lowest, so we have absolute minimum and absolute maximum. So this point here, since this is the highest, so we can say we have absolute maximum of, then we refer to the y value, absolute maximum of 0.9 at x equals negative 1.5. So the highest value of our function is at 0.9 at the given value of x, negative 1.5. So that's our absolute maximum. Then this point here, that is our absolute minimum. So we have absolute minimum of, then what's the y value, or what's the value of our function at that particular point? Negative 6.1 at x equals 0.9. So there. So that is how we identify the absolute minimum and absolute maximum. Okay? We also have what we call as the critical numbers. So let f be a function defined at x sub 0. We say that x sub 0 is a critical number if. So we have to look at these two conditions. First, if we get the first derivative and then we substitute that value, that particular value of x, it will be equal to 0, then we can say that x sub 0 is a critical number. Okay? Or, if we substitute x sub 0 to our first derivative, you will get an undefined, or it does not exist, or we can say that f is not differentiable at x sub 0, then x sub 0 is also a critical number. So these are just the two conditions that we have to consider in order for us to determine if the given value of x is a critical number or not. Now take note, to find the critical numbers of a function, we can follow these steps. So first, we differentiate the function, or we get the first derivative. After that, find the value of x where f prime of x is equal to 0 or f prime of x does not exist. So again, just get the derivatives. After that, we identify the value of x where our first derivative will be equal to 0 or does not exist. So let's find the critical numbers of this given function, x squared over x minus 2. Since we're finding the critical numbers, first step that we have to do is to differentiate. So since this is a rational function, we have a numerator and denominator. That means we have to use the quotient rule. So let's use the quotient rule to get the derivative of this. So low d high minus high d low all over low squared. Okay, so let's just get the derivative of this. X minus 2, derivative of x squared is 2x, minus, then we have the x squared, derivative of x minus 2 is 1, and then the denominator, x minus 2 squared. Then just multiply everything in the numerator. So distribute. So just multiply everything in the numerator. Distribute this one. So you have 2x squared minus 4x minus x squared all over x minus 2 squared. Okay, then let's simplify the numerator. So we have f prime of x is equal to x squared minus 4x over x minus 2 squared. Okay, so this is now the first derivative. So now, after we're done getting the derivative, next thing that we have to do is to identify at what value of x will this first derivative be equal to 0. So that is what we want to identify. But since this is a rational function, so we have to consider the numerator and denominator. So what we will do is, whenever you're dealing with rational function, you have to equate the numerator and denominator to 0. So let's see. So we have x squared minus 4x equal to 0, and then we will be solving for x. So let's start with this one. So you can factor out x. So you have x minus 4 equal to 0. And then equate each factor to 0. So you have x equals 0. The other one is x minus 4 equal to 0. So we have x equals 4. So we have these two values. These are our x values, 0 and 4. Now to check whether these are our critical numbers, since this is a rational function, we still have to check whether it's part of the domain of the original function. Because as what we know, if the original function is a rational function, there are certain restrictions when it comes to the domain. For example, if it makes our denominator 0, or if it makes our function undefined, of course, it's not part of our domain. So in order for us to determine if these two values are really critical numbers of our function, so we have to check if it will make our original function f of x equal to 0 for the denominator. If not, then we will consider them as our critical numbers. So if we substitute 0 to our original function, it will be 0 squared over 0 minus 2, which is not equal to undefined function. So that means x equal to 0 is part of the domain of our function, and this is considered as our critical number. Let's check also for x equals 4. So if you substitute 4 squared over 4 minus 2, so this will be equal to, again, not an undefined function. So therefore, this is again part of the domain. And we can say that x equals 4 is a critical number. So we're not yet done. We also have to check the denominator. So let's equate the denominator to 0 as well. And then get the square root of both sides. So we have x minus 2 equals 0, x equals 2. Now to check if x equals 2 is really a critical number, let's substitute it to our original function. So if you substitute that one, it will become 2 squared over 2 minus 2. So as you notice, our denominator here will become 0. It means that 2 is not part of the domain of our original function because it makes our denominator 0, or it makes our function undefined. So in the first place, this value of x is not part of our function. So therefore, it is not considered as a critical number. So for our final answer, the critical numbers are critical numbers. So we only have x equals 0 and x equals 4. So that will be our final answer. So next, let's discuss this theorem related to absolute extremas. So we have the extreme value theorem, and this is the theorem that guarantees the existence of absolute or the global extrema of a function on a closed interval. So what does it say is that if f is a continuous function on a closed interval ab, then f has absolute extrema, both absolute minimum and absolute maximum on this interval. So this just means that all of the function, or all of continuous function on a closed interval ab, automatically it will have an absolute extrema, both the minimum and the maximum. Now, how are we going to find the absolute extrema on the closed interval? So given an equation, the absolute extrema of a function f, either minimum or maximum on a closed interval ab, can be found by following these steps. So first is we determine first the critical numbers of our function f. So after determining the critical numbers, we have to evaluate our function f at the critical numbers and the endpoints of our interval. So if you have one critical number only, so you evaluate that one critical number, or you use that one critical number to evaluate your function as well as the two endpoints. So you will be evaluating 3 points. If you have two critical numbers plus the two endpoints, so you have to evaluate 4 times. Okay? And then lastly, we just have to observe which one is the least value and which one is the greatest value, because that will give us now the absolute minimum and the absolute maximum of f. So the least of these values is the absolute minimum, while the greatest of these values is the absolute maximum of f on that certain interval. Okay, so let's try this example. Determine the absolute extrema of the function f of x equals x squared minus 8x plus 12 on the interval negative 5, 5. Okay, so first thing that we have to do is to identify the critical numbers. And in order for us to identify the critical numbers, we have to find the derivative. So let's get a derivative of our function. So that is 2x minus 8. And after getting the derivative, we just have to identify at what value of x will this derivative be equal to 0. Okay, so it will not be undefined in this one, because all of the numbers or values of x is defined for this particular kind of equation. So we're just going to identify at what value of x will be our first derivative equal to 0. So let's just substitute, or let's just equate 2x minus 8 is equal to 0 and then solve. So this is 2x equals 8, or x is equal to 4. So that is our critical number. Now, after that, we have to evaluate our function using the critical number as well as the endpoints of our function. So we now have the values of x. We have 3 because there's only one critical value or critical number, and then the two endpoints. So you have negative 5, and then 4, our critical number, and then 5, our endpoint. And then we're going to identify the value of our function at these given points or values of x. So let's solve first for negative 5. So f of negative 5, so you have negative 5 squared. So we will substitute it to the original function. Minus 8 times negative 5 plus 12. So the value that we will get here is 77. And then next, so let's write here 77. Let's solve for 4. So you have 4 squared minus 8 times 4 plus 12 equals negative 4. So you have negative 4 here. And last, for 5, so you have 5 squared minus 8 times 5 plus 12 equal to negative 3. So we have negative 3 here. Now, after you identify the value of our function using our endpoints and also the critical number, we can now define our absolute maximum and absolute minimum. So you just have to look at the corresponding y values or function of our f of x for each corresponding x value. So for the absolute maximum, we just have to identify which one is the greatest value, and that is 77. So that means we have absolute maximum of 77 at x equals negative 5. So again, that is our absolute maximum. So we have an absolute maximum of 77 at x equals negative 5. How about the absolute minimum? So you just have to look at the lowest value, and that is negative 4. So we have absolute minimum of negative 4 at x equals 4. So there you go. We're able to identify the absolute extrema of our function. So we have the absolute maximum of 77 and absolute minimum of negative 4. And we also have a theorem for our relative extrema. So if f has a relative extremum on an open interval at x sub 0, or a particular value of x, then that value of x is a critical number of f. Okay? If f has an absolute extremum on an open interval, then it occurs at the critical number of f. So, here you can see the relationship of the critical number and our extrema. So, the extrema are just our critical points, but not all critical points are considered as extrema. So, how are we going to identify our relative extrema? So, we have what we call as the first derivative test. Suppose x sub 0 is a critical number of a continuous function f. If f prime changes from positive to negative at x sub 0, then f has a relative maximum at x sub 0. Okay. So, later on, we will check the values of our derivative of the function from the left and from the right of our critical number. And we will observe the sign. If our derivative changes from positive to negative, then that means we have a relative maximum at that critical point. But if it changes from negative to positive at that particular point, then our function has a relative minimum at that critical number. Okay, so later, I will give you an example for this one. So we will check how are we going to know if we have a relative maximum or a relative minimum at a certain critical number. Other ways that f might have a relative extremum at x sub 0 is if it is constant on one side or both sides of x sub 0. That is, when f prime is 0 on one or both sides of x sub 0. Okay, so we can also consider that one. Or, lastly, if f prime is both positive on both sides of x sub 0 or negative on both sides of x sub 0, then f has no relative extremum. So there's no relative extremum if both sides are negative or both sides are positive. So let's find all relative extrema of the function f of x equals 2x squared plus 8x minus 11. So what you will do is you have to get the critical number first. So let's get the derivative. And that is 4x plus 8. Okay, so that's the derivative of our function. Next, so we have to identify at what value of x will this derivative be equal to 0. So we have 4x plus 8 equal to 0. That is 4x equals negative 8, or x is equal to negative 2. So that is our critical number. Okay, now that we already have the critical number, we have to check now, or we have to use or perform the first derivative test, wherein we check for the sign of our derivative from the left and from the right of our critical number. So since our critical number is x equals negative 2, then we have to determine the signs of the values of our f prime of x at x is less than to negative 2 and at x is greater than negative 2. That means we are checking for the signs of the values of our first derivative from the left and from the right of our critical number. So you just have to choose a number that is less than negative 2, a number that is greater than negative 2. So it's advisable if you will just get the 1 unit after or before and after our critical number. So here, for x is less than negative 2, let's consider x equals negative 3. Okay, so we will use this. So this represents now the x less than negative 2. And then for x greater than negative 2, so we can use x equals negative 1. Now we will be using these values to evaluate the first derivative. So this will now give us the sign of the values of our function or the first derivative from the left and from the right of our critical number. So let's evaluate. First, let's have the negative 3. So let's use this. So 4 times negative 3 plus 8. Evaluate that one. So you have negative 4. Okay? And then, also, f prime of negative 1. So you have 4 times negative 1 plus 8. or this is positive 4. Now, we already have the sign from the left and from the right of our critical number. So, remember, this one, the negative 3, this is from the left of our critical number, and this one is from the right. So, in order for us to check whether our first derivative changes from negative to positive or positive to negative is, we will be looking at it from left to right. Okay? So, the value of our function is negative 3. We use negative 3 as our x. And then we also use the negative 1 as our x. So, our function, or the first derivative, the sign, if x is negative 3, is negative. And if x is negative 1, the sign is positive. So, from left to right, it changes from negative going to positive. Now, if that is the case, if our f prime of x changes from negative to positive, then that means we have a relative minimum at x equals 2 or negative 2. Okay, so that means we have this relative minimum at x equals negative 2 because we saw that from negative, it changes to positive. We're talking about the derivatives as we consider the less than negative 2 and greater than negative 2. Now, how are we going to know what is the value of our function at that particular value of x? So what you will do is you just have to substitute that value of x to our original function so that we can identify what is the value of our function at that particular point. So we have f of negative 2. Let's substitute here. So you have 2 negative 2 squared plus 8 negative 2 minus 11. So this is negative 19. So what now is negative 19? So that is the value of our function at x equals negative 2. And we know, based on the first derivative test, we know that we have a relative minimum at that point. So therefore, this negative 19 is the relative minimum of our function. So we can say the function f has a relative minimum of negative 19 at x equals negative 2. Okay, so there. So we're able now to identify the extrema or the relative extrema of our function. Or in particular, we have here a relative minimum of negative 19. Okay? So that is how you identify the relative extrema of a function. So that is how you also apply the first derivative test. So that's it for today. I hope you learned something about the critical points as well as the extremum of the function, how to identify absolute extrema and also relative extrema of a certain function, and see you next time.